All right, everyone. Hello to the makeup video. Um, should be a short one. I think I'm not going to do like a full 2 hour lecture. I'm just going to do I'm going to wrap up section 4.6 for those who need it, and we'll just do section 5.1. Okay. So just a kind of I don't know disclaimer. I'm teaching two sections of this course now. So I picked up a second section halfway through. So for my 8 a.m. class, we're going to finish 4.6. I think we finished 4.6 in the afternoon class. So just a little bit of a review. Should only take a few minutes, and then we'll all be on the same page. We'll move on to section 5.1 together. Okay. So remember what we're doing in section 4.6. It's change of basis, essentially. We're working in one basis, and we want to change to another basis. Okay, and in both classes, we talked about how this works. I have a basis B. Let's say I have everything in basis B, and I want to convert to basis C. Okay. Well, if basis B is B1 through Bn and C is C1 through Cn, what do I do? I'm going to figure out how to write each of these basis vectors in terms of C. Okay. And remember what those look like. So B1 in terms of C is, the notation we use is this. B2 in terms of C is this. Bn in terms of C is this. Okay. And then what we do is we make a matrix where the columns are exactly these coordinate vectors. Okay. What do we use this matrix for? Okay. Once we figure out what this matrix is, I can multiply any vector in B coordinates by that matrix, and it's going to convert it to C coordinates. Okay. So this type of thing is good for if we have to do like a lot of conversions. Let's say I have a lot of vectors in B coordinates that I want to convert to C coordinates. Okay. Maybe dozens or hundreds of them. Okay. I don't want to convert all of those things individually. So what I do is instead I just convert the basis vectors, okay, B1 through Bn. Once I do that kind of groundwork, okay, I have a matrix, and now all I need to do to convert all these other vectors is I just need to multiply their coordinates in B by this matrix. So it's a real time saver. Okay. So I think in the morning section we covered that logic, and we kind of covered how we develop this matrix and what this means. Okay. And I think we even got as far as doing an example. Okay. But here's the theorem. Okay. So this matrix that we're making, okay, is the notation we use for it is this. If we're converting from B to C, okay, the arrow goes from B to C. So this stands for the matrix that allows us to convert from B to C. So again, if we multiply that matrix by any vector in B coordinates, it converts it to C coordinates. So this matrix is called the change of coordinate matrix, also known as the change of basis matrix. Okay, so let's do another problem. I know we did a problem in both classes on how to do this. Let's look at one more problem just to get on the same page, kind of refresh ourselves on how to do this, and it'll kind of naturally lead into the last theorem of the section. Okay, so let's do number 8 from the textbook. Okay, so I'll write it out for you guys. Let's go to a new page. We have two different bases for R2. I want to find, problem 8 asks us to find two different things. It asks us to find the matrix, the change of basis matrix from B to C. Okay, so I want to convert from the B coordinates to the C coordinates. And we also want to find the opposite direction. We want to find C to B. Okay. So let's start with this first matrix. Okay, let's start with this. What do I know from my theorem about what this matrix is? What do I know from the early part of the section? This is going to be a matrix. What are the columns of the matrix? I'm going to take B1 and rewrite it in terms of C coordinates. And then the second column is going to be B2, again, rewritten in terms of C coordinates. Okay. So now I want to figure out these vectors. Okay. What are these vectors? Well, if I wanted to find B1 in terms of C, how do I do that? I make a matrix out of my C vectors. And I make it an augmented matrix, and I plug in B1 on the other side, in that augmented column. Now think about what happens when I solve this matrix. It's going to give me coordinates. It's going to give me variables, right? It's the variables I multiply these vectors by to get this. Okay. In other words, it's the coordinates of this vector in terms of these. That's exactly what I'm looking for, right? Okay. Now I want to do this process for this vector B1, and I also want to do it for the vector B2. So maybe you're thinking, oh, this sucks. I got to do this same process two times. You know, I got to do it once for the B1 vector, and I got to do it once for the B2 vector. Okay. We do want to find both of these vectors in terms of the C basis, but there's a shortcut. We're just going to do one matrix. And in the augmented side, we're going to put both of those column vectors. It's kind of like, it's very similar to the process of how we found inverses, right? When we were finding inverses, we put A on this side, the identity matrix on this side, and we row reduce. And then what we ended up on this side was A inverse, right? It's a similar process. What we do is we put the C matrix here, the C vectors here. I put the B vectors here. I row reduce this until it's I row reduce until the left side is I, and that should make the right side the matrix we're looking for. Okay, so that's the idea. And a little handy, kind of a handy way to remember the order of things. You know, the change of basis matrix from B to C, it's written like this. Okay, I'm going from B to C, where C is on the left. Okay. And then when I'm making this matrix, when I'm setting up this thing to row reduce, okay, what is it? We have C on the left, C on the left, B on the right, B on the right. Okay. Now I just row reduce. Okay. So I'm row reducing this matrix. So let's see, I multiply this row by -4, add it here. Okay, I should get something like that. Sorry about that. I had to take a brief hiatus. So let's see, I need to share my screen. Let's see. Almost. right, where were we? Okay. So we were here. We were row reducing to find the change of basis matrix from B to C. Okay. We had set it up so this is the C stuff, this is the B. All right, so we're row reducing. We're at this step. Okay. Now I'm going to divide the bottom row. I'm going to divide out that -3. To get this. Now I'll eliminate that 1. Okay, so let's see. I'm multiplying the bottom row by -1, adding it to the top row. Okay, I should get that. All right, so what do we have here? This right side should be the matrix I'm looking for. That should be the change of basis matrix from B to C. Okay. Now, the problem also asks us to find this matrix, the opposite direction. Okay, so I could just start the whole process over again, just kind of switching these two and row reducing again to find this other matrix. But there's another way to do it that kind of shows how these two matrices are related. Okay. So think about, all right, let's say I convert from B to C. Okay. All right, so I take this matrix and I can multiply it by any matrix, any vector in B coordinates, and that's going to give me a vector in the same vector in C coordinates, right? Okay. But I should be able to undo this, right? If I can convert from B to C, there's no reason I can't convert from C to B. Okay. So let's say I have this vector in C coordinates. I want to convert back to B coordinates. I would multiply it by this matrix, right? Okay. And my result would be that vector, that same vector back in B coordinates. Okay. But remember this, we have this equal sign up here. So this is this, which is the same thing as this. Okay. And I've multiplied this thing on the left by this matrix. So in other words, what I have is x and b coordinates times this matrix times this matrix. Okay. Now forget about this right side for a second. Look at these. Okay, I have x in terms of b, and x, and these are the same vector. Okay, x in terms of b, x in terms of b. And this is some square matrix. I'm multiplying two square matrices together. All right. Well, I know that this has to be the identity matrix then, right? These two matrices have to give me the, if I'm ending up with the same vector, this thing has to equal the identity matrix. So I have two square matrices that are multiplied together, and it gives me an identity matrix. Okay, so what do I know about these two matrices? They're inverses of each other. In other words, if I have this matrix that converts from B to C, I take its inverse. That should be the matrix that converts from C to B. How does that help us? What we did up here is we found the matrix that converts from B to C. I also want to find the matrix that converts the opposite direction. So I could do my whole process over again, starting from the beginning, or I could just take this matrix and find its inverse. So let's find this matrices inverse. Okay. So what am I going to do? I'm going to row reduce until this is the identity matrix, and this is then going to be the inverse of this, which is the matrix that converts from C to B. Okay. So let's row reduce. Let's see, I divide top row by 3, let's say. Okay, then I have this. I multiply top row by 4 and add it to the bottom row. Okay. I want to eliminate this 2/3. So let's say I multiply the bottom row by 2 and add it to the top row. Okay. And then finally, I can just multiply the bottom by 3. Okay. So I have the identity matrix here. And then this is the inverse of the matrix I started with. So this is the inverse of this. In other words, it should be this matrix. So we have 3, -2, -4, 3, and then the other one would be 3, -2, 4, -3. Okay, so very similar, just a movement of the negative sign in this case. Let's see. Just checking my work here. I might have been off by a negative sign somewhere. Well, we could check. We could check to see if we multiply these matrices together, we should get the identity matrix. Let's see. So 3, -2, 9, -8 is 1. -6 plus 6 is 0. Let's see. -12 plus 12 is 0. 8 minus 9 is negative. Let's see, -1. So yeah, we're off by a negative sign somewhere. So it looks like it should actually be this. And this. So I made a little arithmetic mistake somewhere. Anyway, process is still good. Fairly minor mistake there. So see if you can replicate this and do it without my mistakes. Okay. So that wraps up section 4.6. Okay. The last thing of 4.6 was just that same idea that and there was another example. We did example 9, I believe, in the other class, the afternoon class, and it actually worked out perfectly in that example. Should have just stuck with that. But it's just this idea that, okay, if I have a change of basis in one direction, the change of basis matrix in the other direction is just its inverse. Okay. All right. So that concludes section 4.6. And that is the end of chapter 4. So now we move on to chapter 5. Okay. Chapter 5, we're going to introduce something called eigenvectors and eigenvalues. And it sounds very fancy, but it's pretty straightforward. So for this chapter, we're going to be focused on linear transformations from one vector space to itself. Okay, so linear transformations of this form. Okay, for a T from V to V. And don't be, remember, don't be scared by this terminology of linear transformation. It's the same thing as a matrix in finite dimensions. Okay, so we can think about it as matrix multiplication. I'm going to start talking more. I'm going to start using this terminology of linear transformation more, just because it's more general and it's you can use it in more circumstances. Okay, we don't have to confine ourselves to the idea of a matrix. But if that intimidates you, just kind of think of in the back of your head. Okay, it's the same thing as a matrix. So we're going to think of the effect that linear transformations have. We're going to start by thinking of the effect that these transformations have on individual vectors. Okay. So for example, let's say I have the matrix 1, 0, 0, -1. Okay. What effect does that have on the vectors in the vector space R2? It's going to flip all our vectors across the x1 axis, right? Now here I've drawn this blue vector, and we can see it flipping across the x1 axis. Okay. Some vectors in this vector space are going to be more affected than others, right? So for example, if I have a vector that's just right along that x1 axis, that horizontal axis, it's not going to be affected at all, right? It's not changed at all by the linear transformation. We're going to be very interested in vectors that aren't affected very much by these transformations. Okay. In particular, we don't care if the vectors are scaled up or down, like if they're stretched or compressed, but we're looking for vectors that aren't moved off their line. I'm looking for a vector that's not moved, from here to here. Okay, I don't want that. I want a vector that kind of stays on its same line. Maybe it's stretched out a bit, maybe it's shrunk down a bit, but it stays on its same line. And these things we're going to call eigenvectors. Okay, so this is our formal definition. An eigenvector of an n by n matrix A is a non-zero vector x such that A times x is equal to lambda x. That's a lambda for some scalar lambda. Okay, so in this case, lambda is just standing for some scalar. In other words, when I multiply x by this matrix, it just gets scaled up or down. It gets multiplied by a scalar. Okay. These scalars, these lambdas, we call them an eigenvalue for the matrix A. Okay. And we say that x is the eigenvector corresponding to the eigenvalue lambda. So this is an example of a matrix with an eigenvalue. Okay, so cosine of pi over 3, negative sine pi over 3, sine pi over 3, cosine pi 3. Okay, we got a little trig stuff, but think back to the section, let's see, what was it? It was chapter 2, I believe, when we were writing out the matrices for a transformation, right? So this is just the transformation that rotates our vectors pi over 3 radians counterclockwise around the z-axis. And so, my stuff in the xy plane is getting, not just the xy plane, but I'm in 3 dimensions. What I end up with is like this vertical axis is kind of my axis of rotation, and stuff is going to get rotated around that axis by pi over 3. Okay. So for example, if I have the vector 1, 0, 1, okay, my transformation takes it and rotates it pi over 3 degrees until I end up with the vector 1/2 square root of 3 over 2, 2. Okay, where's that 2 coming from? Notice that we have a 2 here. Okay, so our x3 components are getting multiplied by 2. So we're not just rotating, we're rotating around the z-axis, and then we're multiplying our z coordinate by 2. Okay, so there's a rotation and there's a stretch going on. Okay. But what if our vector is just on that x3 axis? What if it's just a vertical line? What's the effect? Well, if it's just on that x3 axis, there's not much to rotate, right? It's getting rotated around the x3 axis, but it is on the x3 axis. So the only part of this matrix that has an effect is this 2 here. So what happens to my vectors on that x3 axis? They just get doubled, right? We go from 0, 0, 1 to 0, 0, 2. So this vector 0, 0, 1, it is an eigenvector, right? When we multiply it by the matrix, it just gets stretched. It gets doubled by 2. So 0, 0, 1 is an eigenvector of A corresponding to the eigenvalue of lambda equals 2. And in fact, if we looked at this picture a little bit more closely, any vector on this x3 axis is an eigenvector, right? Let's say I start with the vector 0, 0, 3. Okay, what does my transformation do to that? Again, it just doubles it. You know, it would take it way up here to 0, 0, 6. Okay. So any vector on that same line is also going to be an eigenvector. And it's going to be an eigenvector for that same eigenvalue. Okay. So what we're going to end up with, is a subspace. The eigenvectors are going to give us a subspace. Okay, but we got to be a little bit careful. So let's see. What do we have? If x is an eigenvector for the linear transformation, then any multiple of x is also an eigenvector, and it's an eigenvector for that same eigenvalue. Okay. So think about this. We can do it in terms of matrices if that's comfortable. So x is an eigenvector corresponding to eigenvalue. You know, let's say the eigenvalue is a. Okay. Let's take a multiple of x. Let's say look at cx, and let's do a times cx. Well, remember our properties of matrix multiplication. I can pull this c outside. Okay. Now, since x is an eigenvector, okay, this a times x, well, what is that? A times x is little a times x, right? So I have c times a times x, and I can just rearrange this. Okay. In other words, I have a multiple of x, I multiply it by the matrix, and I just end up multiplying this thing by that same eigenvalue. Okay. In other words, these eigenvectors, if I'm talking about the eigenvectors for a particular eigenvalue, it's closed under scalar multiplication. Let's look at point 2 here. Let's say x1 and x2 are both eigenvectors corresponding to the same eigenvalue. Let's just call it lambda. Let's look at the sum of x1 and x2. Okay. I take the sum of x1 and x2 and multiply it by a. Well, again, from the properties of this, matrix algebra, we know we can split that up into these two terms. Now, since x1 and x2 are both eigenvectors, a times x1 is just lambda times x1. A times x2 is just lambda times x2. So what I end up with is lambda x1 plus lambda x2, factor out the lambda, and I have lambda times x1 plus x2. In other words, this set of eigenvectors that correspond to lambda, it's closed under vector addition. Okay. And remember, those two conditions are all I need for a subspace, right? So our set, we could write it like this. Let's say B is the set of vectors in V such that A times X is equal to lambda X for that particular lambda. Okay. What do we know? We know B is closed under scalar multiplication. B is closed under vector addition. The only other thing, depending on how you define the subspace, we should check that the zero vector is in there as well. It is. The zero vectors in every set of this type of these, when I'm talking about eigenvectors. Think about A times the zero vector. That's the zero vector, right? Well, the zero vector is, that's equal to the lambda times the zero vector for any lambda. So it's always in there. Okay. So what do we know? What does this stuff combine to give us? We can sum it up in this theorem here. Let lambda be an eigenvalue of our linear transformation. The set of all eigenvectors corresponding to that particular lambda forms a subspace of our vector space. We call it the eigenspace corresponding to lambda. Okay. So let's see an example. Okay, this matrix here. Okay, nice simple matrix. We're going to talk about how we figure this. I'm just going to give you some facts and you can check them yourself. We're going to see how to figure them out on our own in a little while. Looking at this matrix, the vectors 1, 0, 0 and 0, 0, 1 are eigenvectors corresponding to the eigenvalue of 3. Okay. So in other words, if I multiply this matrix by either of those vectors, what do I get? I get the same vector multiplied by 3. You can check all these statements on your own. So these are eigenvectors corresponding to 3. On the other hand, this is the eigenvector corresponding to 2. If I multiply that matrix by this vector, I get the same vector multiplied by 2. Okay. So the set of all vectors that are, these are not the only vector. These are not the only eigenvectors. The set of all vectors, the set of all eigenvectors for lambda equals 3 forms a subspace, and it actually ends up being this vertical plane, the x1, x3 plane. Okay, so this. Okay. Also, the set of all vectors that correspond to eigenvalue 2, it's also subspace. It's a smaller subspace. It's just a line. It's just that line along the x2 axis. Let's see. We'll do this theory, and there's some problems in here as well. We're getting to some problems. Okay. All right. So we have the idea of eigenvectors, eigenvalues. Okay. We've introduced them. we want to start figuring out how, like if I'm given a matrix A, I want to figure out what the eigenvectors are, what the eigenvalues are. Okay. This is information I want to find. Okay. It's kind of a two-step process. Usually, if I'm starting from scratch, what I would do, it's actually your first step would actually be to figure out what all the eigenvalues are. Okay. Once you know the eigenvalues, you can find the eigenvectors for each of those values. Okay. Step one, it's not too hard, but for whatever reason, the book introduces it in the next section. Okay. So let's skip step one for a second. And let's see how we do step two. So, pretend we've done step one. Pretend we know all the eigenvalues of our matrix. Okay, I know the eigenvalues, but I don't know the eigenvectors. So now I want to find those eigenvectors. Okay, and let's look at a specific eigenvalue. Let's say that lambda is a specific eigenvalue. And we know it's an eigenvalue of our matrix. How do I find the eigenvectors? Okay, and in particular, I want to find the basis for that eigenspace corresponding to that lambda. Okay. How do we do that? Okay, it's pretty simple. It ends up just being a row reduction of some type. All right, but let's see how we develop it. Okay, so we know that lambda is an eigenvalue for x. Okay. In other words, there has to be some vector x such that a times x is equal to lambda times x. Okay. By the way, I don't think I put it here. Let's just kind of put it. If lambda is an eigenvalue for A, then there is a non-zero vector x such that ax equals lambda x. Okay. That x has to be a non-zero vector. Okay. All right. If we had a zero vector, this would all be, mush. Okay. So lambda, we know that lambda is an eigenvalue of our matrix. That means there's this non-zero vector x such that a times x equals lambda x. Okay. Well, lambda x, it might seem, pointless to do this, but it's going to help us. Lambda x is the same thing as lambda times the identity matrix times x, right? You can do that quick calculation yourself and reassure yourself. Why do we do that? We want to be able to factor a matrix out of both of these terms, basically. Okay. All right. So we're just rewriting this. We can just plug that, plop that identity matrix in there. And that's going to allow us to do the next couple steps. Let's move everything now to one side of the equal sign. Okay, so I'm going to subtract this term from both sides to get this. Okay. And then notice there's an x on both of these terms. We can factor out that x. Okay. What do I get when I factor out x from here? Well, I'm just left with a matrix A. What about when I factor x from here? I'm left with a matrix lambda times the identity matrix. Okay. So in other words, I have x times A minus lambda I. Okay. And all of that is equal to the zero vectors, right? Or to the zero vector. Okay, so now this is just a homogeneous system. Line 4 is just a homogeneous system. We know how to solve those, right? We can solve those for all the solutions, all the x's that make this work. the free variables in there are going to give us our, remember the free variable vectors are going to give us our basis for the solutions of the homogeneous system. Okay. So in other words, the free variable vectors are exactly the vectors I'm looking for. They're my eigenvectors and they form a basis for the eigenspace. Okay. So let's see an example. This is one of the problems for the textbook. I forget exactly which one it is. Okay. So we have A is equal to this matrix and lambda is equal to -4. What is the problem statement? We want to find a basis for the eigenspace corresponding to the eigenvalue lambda equals -4. Okay. So let's take this and let's go to a new page and do the work. Okay. So what do I know? I know that my eigenspace is going to be the solution to what? It's going to be the solution of the homogeneous system A minus lambda I x equals 0. Okay. Well, first of all, what's our lambda? The lambda we're looking at is -4. In other words, I'm looking for the solutions to this system. Let's go ahead and write this as a matrix. Okay. What is A plus 4 times I? Well, A, we already have A, right? 3, -1, 3. -1, 3, 3. Six, 6, 2. What's 4 times the identity matrix? Okay, in other words, 4, 4, 4. All right. What is this? This, I'm writing everything out to be clear, but once you see how it works, you can do it just in your head usually. The solution is, or this sum is 7, -1, 3, -1, 7, 3, 6, 6, 6. Metal. Okay, so now I'm solving. This is my A plus or A minus lambda I matrix, right? Okay. Now I want to solve the homogeneous system. This. I have my matrix. I want to solve the homogeneous system. I could do the augmented matrix column, but remember, this last column for homogeneous systems is just completely redundant. Okay, so I'm just row reducing this matrix. Okay, let's take this row and subtract it from the top row to get a 1 in that top place. Let's see, so 1, -1 minus 6 is -7. 3 minus 6 is -3. Notice that these are the same row, just with a different sign. So I can, I know that row is going to get canceled out completely. Okay. There's ones here or sixes here, so I know I can divide out the 6. Okay, so I get this. Now let's continue. Let's eliminate this 1. Let's see, 1 plus 7 is 8. 1 plus 3 is 4. Okay, in other words, 1/2. Let's eliminate that -7. It should be just +1/2, I believe. Okay. In other words, let's see, I have a pivot column here, pivot column here. x3 is free. So the solutions to my homogeneous system would be this. Okay. So this vector here, that's the basis for my null space for A minus lambda I. Okay, which is the same thing as this is the basis for the eigenspace. For my lambda equals -4. Okay. So let's double check that. Let's see, what problem was that from the book? We're looking at chapter 5. What was the matrix we started with? 3, -1, 3. That looks like it was problem 14. Looking at my super duper instructor solution manual. Need to scroll to chapter 5. Look for 14. Yep, -1/2, negative out 1/2, 1. Perfect. All right. So we see how to find the basis for an eigenspace. Okay. Let's say that we had done some other problem, and the solution we got for that homogeneous system, maybe it was maybe it was something like this. Okay. Well, then the basis for the eigenspace would be these two vectors. Okay. So, yeah, not too terribly difficult. There's only one last type of calculation we need to be able to do. It's not too much of a calculation. So we've seen, okay, if we know the eigenvalue, we know how to find the eigenvectors now, the basis for that eigenspace. What if I'm given a matrix and a vector, and I'm asked the question, okay, is this vector, is it an eigenvector of our matrix? How do we do that? It's super simple. It's even easier than what we just did. Okay, so we're given a matrix A, we're given a vector X, and we're asked if X is an eigenvector of A. What do? We just multiply A by that vector X. And then we look at the result. If X is an eigenvector, the result should be some multiple of X. Okay, it should be like lambda times X. So for example, I'm given these two things and I'm asked, is X an eigenvector of A? If so, for what eigenvalue? Okay, so how do I check? I just multiply A by X. Okay, so I do 4, 2, 2, 4. I multiply it by X, -1, 1. I'm going to look at the result. Let's see, 4 times -1 is -4, plus 2 is -2. Okay. 2 times -1 is -2, plus 4 is 2. Okay. So is this a multiple of X? Well, X is this. Yeah, this is just a multiple of X. What is the multiple? Well, this is equal to 2 times X. Okay. So X is an eigenvector of A. And it corresponds to eigenvalue 2. Wrap up the section with just a couple theorems. Okay. The eigenvalues of a triangular matrix are just the entries on its main diagonal. Okay. Pretty simple statement. Okay, if I have a triangular matrix, something, I did a 3x3 example here, but this holds for any dimension. Okay. If it's this form, okay, upper triangular, lower triangular, doesn't matter. The eigenvalues are just these terms on the diagonal, these numbers on the diagonal. So easy. Proof would be pretty simple. We can talk through it real quick, not super important. But we can checking that these A, B, and C, checking that they are eigenvalues is really easy. The slightly more difficult thing is making sure those are the only eigenvalues. Okay. So it's really easy to check that A, B, and C are eigenvalues. Just multiply the matrix by the standard basis vectors, E1, E2, E3, and look at what you get. When I multiply it by E1, the result should be A times E1. When I multiply by E2, the result should be B times E2, and so on. So all those are eigenvectors. The more difficult question is, okay, are there any other eigenvalues kind of hiding in the matrix? Okay. Are there any eigenvalues besides A, B, and C? The answer is no. How can we show that? Assume there is some other eigenvalue. Assume D is an eigenvalue. Okay. Well, if D is an eigenvalue, there should be a non-zero vector x such that AX equals DX. In other words, A minus D times the identity matrix times X should be equal to the zero vector. But think about the solution to this homogeneous system, right? It looks like this. Okay, I've written that augmented column there just for clarity. Okay. So our system, the solution to our system should look like that. But notice that, let's see, notice that there's a pivot in every column. Okay. If D is not, if we're assuming that D is not equal to any of the other values, it's not equal to A, B, or C. Okay. So none of these should be zero, right? Because we're subtracting two different numbers in each term. Okay. So we have a matrix with three pivot columns. Okay, three pivot columns. Okay. In other words, the only solution here is the trivial solution. Okay, so X is equal to the zero vector. But remember, we're looking, if D is an eigenvalue, this X, there has to be a non-zero vector X. But we're seeing that the only possibility is for X to be the zero vector. Okay. Or you could look at it through the lens of back substitution, Okay, we have C minus D equals zero. Okay. Okay. Or C minus D times X3 is equal to zero. Okay. So in other words, X3 has to equal zero. And then substituting back upward, we would see that X2 and X1 have to be equal to zero as well. So there's no non-trivial solution. So D is not an eigenvalue of A, of the matrix A. So there are no other hidden eigenvalues in a triangular matrix. It's just the stuff on the main diagonal. Last theorem. Oh, and there are problems in the book that corresponds to this theorem. So for example, problem 16, for instance, not 16, problem 17, 18, it asks you to find the eigenvalues of the matrix. If you look at both of those matrices, they are actually triangular matrices. So for example, 17 is the matrix 0, 0, 0, 0, 2, 5, 0, 0, -1. Well, this is an upper triangular matrix, right? Okay, so the eigenvalues are just the stuff on the diagonal. So 0, 2, -1. Easy peasy. And it's perfectly fine for 0 to be eigenvalue. Maybe that seems strange, but yeah, there's nothing wrong with that. 18 is similar. Okay. Last theorem of the section. If V1 through VR are eigenvectors of A that correspond to distinct eigenvalues, then the vectors are linearly independent. Okay. So V1 through VR are eigenvectors, and each one is an eigenvector for a different eigenvalue. Okay, then those eigenvectors are linearly independent. The theorem here, or the proof of the theorem, is interesting. It's a little complex, so I won't go through it, but I won't go through it in class. It won't be, that kind of thing won't be required. But I think it is. This class is kind of on the borderline of proofs, right? Like 3105 is not proof-based course, and 3106, which is basically the same course. It's the same course, but with proofs. So you're kind of on the borderline of proofs. So they're not required, but I do highly suggest you look at the proofs. So, go check out the proof for this theorem. See if you can keep track of what's going on. See if you can work your way through it and understand it. I think it'd be good. Good for your mathematical development if you're interested in that kind of thing. That wraps up section 5.1. In the textbook, there's also this little paragraph on eigenvectors and difference equations. We're not interested in that. So that wraps up this section 5.1. So we'll end there. I lost track of time. I don't know how long we went, but I think this was a short lecture. So for both classes, we'll start with, we'll probably do some problems from 5.1 on Monday and then go into 5.2 material. Have a good weekend.